Okay, so let's get started. So, hello and welcome everyone to week 5 of interactive live sessions for the course on Computational Fluid Dynamics for Incompressible Flows. So, the course is being taught by Professor Amaresh Dalal from the Department of Mechanical Engineering, IIT Guwahati. My name is Debjit. I am a PMRF scholar at IIT Madras and I'll be the TA for this course. So, like every other week, we will be discussing some sample problems related to the particular week of the course. So, today is week 5. We will be discussing about the different discretization and solution techniques of parabolic equations. So, without further ado, let us get started. We will move to question number 1 of today's session. Question number 1 is asking us what is the advantage of the implicit method over the explicit method for solving parabolic equations? Is it there are four options given here. So the first option is it is unconditionally stable. Option B is it can have a larger time step limit. Option C is it is more accurate. And option D is it is both A and B. That is, it is both unconditionally stable and it may have a larger time step limit as well. So take your time and try to land on the correct solution. And once you have done so, you can type in your answer in the chat box or you can unmute yourself and answer. So question number 1 of today's session is asking us what is the advantage of the implicit method over the explicit method for solving parabolic equations? Is it A, it is unconditionally stable? Is it B, it can have a larger time step limit? Is it C, it is more accurate? Or is it D, both A and B? So let us have a look at the solution. The solution is option D, which is both A and B. So what we do in the implicit method is that, let's say we will take the model parabolic equation which we saw in the lecture. So it's something like dou phi dou t is equal to some diffusion coefficient gamma into dou square phi dou x square. Now there are various ways of discretizing it as we saw, and so one of them would be we will take something like this phi n minus 1 minus phi n, both located at spatial location I, divided by delta t, which is our time step. And now this should be equal to this gamma into, we will take delta x square in the denominator, and in the numerator we shall have I plus 1 minus 2 phi I plus phi I minus 1. Now one easy simpler way, more compact way of writing this would be to write it like this, but anyway we are writing the fully expanded form here. Now the thing is, if these values on the right hand side are taken at the n plus 1th time step, then all of these are unknown and we have to find them in terms of the known, which is the phi in, or the values of phi at the nth time step. Then this kind of a method is known as an implicit method because there are multiple unknowns in this equation. So what would be the explicit then? In explicit form, we will have only one unknown and rest all known values. So this would be written as, I am erasing this for now. I'll write it over here. So delta x squared pi n plus 1, whatever it is that we take. So this would be exactly similar with one small point of difference, which is we will take these values at the nth time step. So what this results in is that all these are known values. The only unknown over here is this phi I n plus 1. And now we calculate this in terms of all the other known values in the equation. So this is the explicit form of the form of solving parabolic equations. So now these have, each of them have their own pros and cons. The explicit one is easy to formulate and solve, and whereas the implicit one requires a bit of more math since there are multiple unknowns involved in each equation, but it's pretty straightforward. You generate the coefficient matrices and then try to solve them. There are then again you'll have various ways of solving that matrix. You can do it iteratively, you can do it directly. Anyway, now one of the main advantages of using implicit techniques are that they are unconditionally stable. Explicit ones can be stable, but under certain specific conditions, which we will talk about later during today's session as well. But implicit techniques, they are unconditionally stable. It doesn't matter what time step or spatial uh, division you take. The mesh size or grid size, that's what I'm talking about. So the delta x and delta t, it's completely uh, you know uh, independent of that. It is unconditionally stable. So that's what lets us have a larger time step limit as well. There is no limitation on how large a time step I can take. Although for accurate solutions, it is suggested to have a small time step. But as far as the system of equations are concerned, it can have any large time step as possible. So that's why both A and B would be the correct answer. So option D would be the correct solution to pick over here. Okay. Any doubts on this one? So the question we had asked is, what is the advantage of the implicit method over the explicit method for solving parabolic equations? So we had these three main statements in which it is more accurate, does not have to be true, but these first three statements, statement A and B, are true. So that's why option D, which is saying both A and B are correct, would be the correct solution to this question. Okay. All right, so if there are no doubts, we will move along. We'll move on to question number 2 of today's session. So, question number 2 is asking us which of the following stability criteria is used for the explicit method? Is it option A, CFL condition? Is it option B, von Neumann stability analysis? Is it option C, maximum principle? Or is it D, none of the above? So have a nice read of the question, and then once you have figured out the correct solution, pick your option from the four options given below. You can either type in the chat box, or it's better to unmute and answer if it's possible. And any doubt whatsoever, you can ask. Any clarification of the particular question involved or anything, any other relevant topic, please don't hesitate to bring it up. We are here to have a discussion, so we will go ahead with it.
I think the answer is B, von Neumann stability analysis.
Yes, would you like to say something?
Option B, is it
I'm
correct?
sorry, you are not audible. Uh,
Hello?
is it my problem? Let me check once. I'm not able to hear you. Option B, okay. First, give me a moment to check my system. Uh, can anyone unmute and say something just to check whether it's something wrong with my system or not? Dr. Pallavi was trying to talk, but I couldn't hear her. I'm still unable to hear you.
Option B.
Still unable, sorry. Let me check. Can anyone else say something? Okay, you are also talking, but I'm unable to hear. Let me leave this call and rejoin. Please hold
Sir,
on. Okay,
Madam is
please
telling
continue.
the answer B.
Yeah, hello. Anyone stop so that I can check if the problem is resolved or not?
Hello.
Okay, I'm still unable. It's okay. I have a different system. I'll try to use that one.
Oh,
Sir, Madam is
Hold
telling
on.
answer B.
I think you are also not audible to sir.
I'll close this. Yeah,
Yeah,
hello.
hello.
Can you
Can you
hear me?
hear me?
Am I?
Am I audible?
Yes, yes.
Okay,
Okay,
now I
now I
can
can
hear you
hear
as
you
well.
as well.
Awesome. So
So
Okay.
let's
move
move
along.
along.
I'm sorry
I'm sorry
for
for
the
the
technical
technical glitch,
sort of.
sort of.
Anyway,
Anyway,
so
so
you were
you were
saying
saying
option B,
option
right?
B, right?
Yes.
Von
For
Neumann
Neumann
stability
stability
analysis.
analysis.
Okay.
Okay.
Anyone
Anyone
else?
else?
Any
Any
other
other
answer?
answer?
Yes, answer B, sir.
Answer B.
Answer B.
Okay.
Okay.
So
So
let's have a look
let's
at the
have a look at the
solution.
solution.
The solution
The
says
solution
option A
says option
CFL
A
condition.
CFL condition. So
I'm
I'm
a bit
a
sorry.
bit
The
sorry. The
options might be a
options
bit
might be a bit
confusing over here.
confusing
So
over
von
here. So
Neumann
von
stability
Neumann stability
analysis.
analysis.
This
This
actually
actually
gives us
gives
the
us the
criteria for
criteria for
stability,
stability,
but the
but
actual
the
condition
actual condition that it that
an
an
explicit method
explicit method has to
sort of
sort
satisfy
of
is the
satisfy is
CFL
the
condition.
CFL
This is
condition. This is
also known
also
as
known as
the full
the
form of
full
it
form
is
of it is
Courant
Courant
Friedrichs
Friedrichs
Levy
Levy
condition.
condition.
So if you
So if
remember
you
the
remember the
first
first
lecture which we
lecture
saw, in
which we
which
saw in which
CFD was
CFD was
introduced,
introduced,
Professor
Professor
Courant was one
Courant
of
was
the
one of the
pioneers of
pioneers
CFD,
of
and
CFD, and
these were
these
his
were
students
his
further
students
down the
further
line.
down the
So
line.
this
So
condition
this
was
condition
named
was
after
named
them.
after them, CFL condition.
So I
So
understand
I
why you
understand why you
guys picked
guys
option
picked
B.
option B.
So
So
the stability
the
criteria
stability
is
criteria
actually
is
found
actually found
using
out
von
using
Neumann
von
stability
Neumann
analysis,
stability
but the
analysis, but the
criteria is
criteria
called
is called
CFL condition
CFL
in case of
condition in case
explicit
of
methods.
explicit methods.
You're not
You're
wrong,
not
so to
wrong,
say.
so to
The
say.
options
The
were a bit
options were a bit
confusing.
confusing.
So sorry
So
about that.
sorry about that.
Okay.
Okay.
Anything you'd like to
Anything you'd
discuss
like to
about
discuss about
anything
anything
outlining this topic?
outlining this topic?
No, sir.
Okay.
Okay.
Then let's move
Then
on to the
let's move
next
on to the
question.
next question.
So question
So
number
question
three of
number
today's
three
session
of
is
today's
asking
session
us
is
which of
asking
the
us which of
following
the
is
following
not
is
governed
not
by a
governed by
parabolic
a
equation.
parabolic equation.
It is not governed by a parabolic equation. So is it option A, Stokes' first problem? Is it option B, boundary layer over a flat plate? Uh, is it option C, unsteady heat diffusion? Or is it option D, steady heat diffusion?
Answer is A.
A. Okay. Any other answers? So Stokes' first problem, can anyone say what it is? What kind of a flow is it? So which of the following physical phenomena are not governed by a parabolic equation? Is it option A, Stokes' first problem? Is it option B, boundary layer over a flat plate? Is it option C, unsteady heat diffusion? Or is it option D, steady heat diffusion? Now, someone pointed out that the answer would be the first one, Stokes' first problem. Now, what exactly Stokes' first problem is that we take an infinitely long plate. Okay, this is infinitely long. And we have some fluid surrounding it. Let's say only the top part we will consider. And what happens is, this is, let's say, the origin. Now, at time t less than 0, this is at rest. So u is equal to 0. Now, just as time t becomes greater than equal to 0, there is a certain constant u imparted to it. So it's as if there is a plate lying like this. It's completely at rest, and then I impulsively start moving it with a constant velocity. So what that does is it creates these velocity profiles like this. So due to viscosity, the momentum of the plate, it slowly diffuses to the layers of liquid or whatever fluid above. So anyway, that is the first option, Stokes' first problem. There are three more options. So boundary layer over a flat plate, what is that? So we have a flat plate like this. We are all pretty familiar with it. Now there is a uniform incoming flow like this, but due to the plate and its viscous effects, one layer gets built up where this flow is slowed down due to viscosity, and that is the layer in which we feel the effects of the boundary, and we call it a boundary layer. And unsteady and steady heat diffusion, you already know. So let's say we'll take this simple 1D rod like this, and we will heat one end of it. So in the unsteady case, there again, before t equal to 0, the entire t would be some t naught. And then after t equal to 0, there would be a boundary. So boundary condition imposed. So let's say if this is x equal to 0, and this is x equal to L. So then only t at x equal to L will be some high T, which is equal to the temperature of this flame. And yeah, that's it. So this causes heat transfer in this direction, and if the temperature profile initially varies with time, so that is unsteady heat diffusion, and once it becomes steady after the initial transients are died down, so then it becomes a case of steady heat diffusion. So which will be the correct answer? We have received only one answer so far. Let's see what others have to say. Which of the following is not governed by a parabolic equation? let's have a look at the
the
actual equations
governing
governing
these
these problems.
problems.
So
So
let's
let's
start
start
from
from
the
the
bottom.
bottom.
So
So
steady
steady
heat
heat
diffusion.
diffusion.
What
What
is
is
the
the
equation
equation
for
for
it?
it?
Can
Can
anyone
anyone
help
help
me
me
with
with
it?
it?
What
What
is
is
the
the
equation
equation
governing
governing
steady
steady
heat
heat
diffusion?
diffusion?
So for one dimensional, sir.
Sorry,
Sorry?
For one dimensional,
for one
For one
dimensional. Yeah.
dimensional, yeah.
dou square x by dou t square is equal to 0.
So
So
dou
dou
square
square
T by dou x square is equal to 0.
is
is
equal to
equal to
0.
0.
Correct.
Correct.
Then
Then
unsteady
unsteady
heat
heat
diffusion.
diffusion,
What
what
would
would,
so
so
let's
let's
write them
write them
down
down
elsewhere.
elsewhere.
So
So
we
we
started
started with D.
this
This
is
is D. Now
let's
let's
go to
go to
C.
C.
Unsteady heat
Unsteady heat
diffusion.
diffusion.
What
What
would
would we
be
be
governed
governed by?
That is no 1 by alpha. Is it?
One by alpha.
Uh, dou t by dou tau.
Dou T by dou T
Yes, yes, sir.
equal
equal to
to this
this same thing, right?
dou
Dou
square
square T by
by
dou
x
x
square.
square,
Yes, sir.
Right?
right?
Yeah.
Yeah.
Yes.
Now the
boundary
boundary
flow
flow
over
over
flat
flat
plate.
plate.
What
What
would
would
be
be the equation
governing
governing boundary layer
over
over
flat
flat
plate?
plate?
So
So
on the
on the
left hand
left
side
hand
we
side
have
we
the
have the
convective
convective
part,
part,
Uh,
and on
and
the
on the
right
right
hand
hand
side
side
what do we
what do we
have?
have?
The
The
diffusive
diffusive
part.
part.
okay.
These are the only equations which
survive.
survive.
Okay.
Sorry,
Sorry,
this
this is
is dy
dy
square.
square.
And
And
option
option
A,
A,
Stokes'
Stokes'
first
first
problem.
problem.
Here
Here
you
you
see
see
there is
there is
only
only
u in
u
this
in this
equation.
equation. There is no v.
So
So
all
all
the
the
flow
flow
happens
happens
only
only
in
in
the
the
x
x
direction.
direction.
But
But
there is
there
no
is no
variation
variation
in
in
the
the
x
x
direction
direction
because
because
this
this
is
is
infinitely
infinitely
long.
long.
So the
So the
only
only
variations
variations
survive
survive
only in
only in
the
the
y
y
direction.
direction.
So
So
if we
if we
start
start
from
from
Navier-Stokes
Navier-Stokes
equation,
equations,
it
it
can
can be,
you know
you know,
simplified
simplified
down
down
to
to
dou
dou
u
u
dou
dou
t.
t.
And
And
yeah,
yeah,
this
this
is
is
unsteady
unsteady
flow.
flow.
So
So
there
there
is
is this
temporal
temporal
term
term
dou
dou
u
u
dou
dou
t
t survives
survives
over
here.
here.
And on
And
the
on the
right hand
right
side
hand
we
side,
have
we
a
have a
similar
similar
dou
dou
square
square
u
u
y
dou y
square
square
sort of
sort of
thing.
thing.
So
So
these are
these
the
are the
four
four
equations.
equations.
Which one
Which one
among
among
them
them
is not
is not
parabolic?
parabolic?
Is it, I think, equation B?
Yes,
Yes,
correct.
correct.
Equation
Equation
D
D
is
is
not
not
parabolic.
parabolic.
Which
Which
kind of
kind of
equation
equation
is
is
it?
it?
It's
It's
elliptic, right?
elliptic, right?
Yes.
So
So
option
option
D
D
would be
would
the
be the
correct
correct
answer.
answer.
Let's have
Let's
a
have
look
a
at
look
the
at the
solution, and
solution, and
indeed
indeed
option
option D is the
correct
correct
answer.
answer.
Okay.
Okay,
So
so
this one
this
is
one is
an
an
elliptic
elliptic
equation.
equation.
The
The
other
other
ones are
ones are
parabolic.
parabolic.
Since the
Since the
question
question
was
was
not
not
governed,
governed, that's why
this
this
elliptic one
elliptic
would
one
be
would be
the
the
correct
correct
answer.
answer.
Okay.
Okay,
So
so moving
we'll
on,
move on
we'll
to
move
question
on to
number
question
four of
number
today's
4 of
session.
today's session.
Which of the
Which of
following
the
is the
following
order
is
of
the order of
accuracy of the
accuracy of the
Twofold-Frankel method?
Twofold-Frankel
So
method? So
Twofold-Frankel method was
Twofold-Frankel
one of
method
the
was one
methods
of the
in which
methods in which
parabolic
parabolic
equations can be
equations can be
discretized.
discretized.
So is it
So is
first
it
order?
first
Is it
order?
second
Is it
order?
second
Is it
order?
third
Is
order?
it third
Is it
order?
fourth
Or is
order?
it fourth order?
Now remember,
Now
I'm talking
remember, I
about
am
time
talking
over
about
here.
time over here.
I should have
So I
mentioned
should have
this. Sorry
mentioned
about
this.
that.
Sorry about that.
So order of
So order of
accuracy
accuracy
in terms
in
of time.
terms of time.
So there are
So there
usually
are
both, right?
usually
Time
both,
as
right?
well as
Time as
space.
well as space.
So
So
this question is
this
related
question
to
is
time.
related to time.
Is it option A,
Is it
first
option A,
order,
first
option
order,
B,
option
second
B,
order,
second
option
order,
C, third
option C,
order,
third order,
or option D,
or
fourth
option D,
order?
fourth order?
First order.
First order.
First order. Okay.
And let's see if we
Let's
get
see
any
if
other
we get any other
answers.
answers.
Yeah. So
Yeah.
which of the
So which of
following
the
is the
following
order
is
of
the order of
accuracy of the
accuracy of the
Dufort-Frankel method?
Dufort-Frankel
Is it
method? Is
option
it
A first
option A
order,
first
option B
order,
second
option B
order,
second
option C
order,
third
option C
order,
third
or option
order,
D
or
fourth
option D
order?
fourth order?
We have one
We
answer
have
in
one
favor
answer
of
in
option
favor
A
of
first
option A
order,
first order,
and we're
and
hoping to
we're
get more
hoping to get
answers.
more answers.
All right. So
All
let's
right,
have a
so
look at
let's
the
have a look at
solution.
the solution.
Solution is
The
option
solution is
B
option
second
B
order,
second order,
and
and
so
so
the order of
the order of
Dufort-Frankel method is
Dufort-Frankel
like
method
this:
is like
order
this.
of
It's order of
second order of
second
time
order
as
of
well as
time as well
second
as
order in
second
space.
order in space.
So
So
how we
how
actually
we
discretize
actually
the
discretize
Dufort-Frankel method is
Dufort-Frankel
something
method
like
is
this.
something like this. So
Start
we
with the
start with the
uh,
uh,
you know
you know
the model
the model
parabolic
parabolic
equation.
equation.
Then what we
Then
do is
what we do is we take
uh,
uh,
we first of all
we first of all discretize
the time
the
derivative
time
in this way,
derivative in this way,
and
and
on the right hand
on the
side
right hand side
we will write
we
down
will write down the
okay, first of all
okay,
there is
first of all,
gamma,
there is
then
gamma,
there is delta
and there
x
is delta
squared
x
underneath.
square underneath.
Okay, so
Okay,
let's
so
talk
let's
about the
talk about the
development of
development of
Dufort-Frankel method
Dufort-Frankel
first.
method first. So
Initially,
initially it started off with
Richardson method,
Richardson method,
which is a
which is a
CTCS scheme.
CTCS
What
scheme.
does
What does
CTCS
CTCS
mean?
mean?
It was central
It was
in time
central
as
in
well as
time as
central
well
in
as central
space.
in space.
Now,
Now,
this equation
this
was
equation
written
was
down
written
like
down
this.
like
So
this. So
we take a
we take
central
a central
difference
difference around time
as well
as well
uh,
as sorry,
not f
not
gamma
f gamma
delta x
delta x
squared
squared
minus 1n
minus 1n
minus 2
minus 2
phi
phi
plus
plus p
I,
and I.
right?
Right.
But this
But this
equation turned
equation
out to be
turned out to be
unconditionally
unconditionally
unstable.
unstable.
So
So
in all
in all
situations, this
situations, this
won't give us any
won't give
result.
us any
So this
result.
was
So this
practically
was
useless.
practically useless.
Now, this
Now,
was
this was
modified
modified using this
Dufort-Frankel method,
Dufort-Frankel method,
in which
in
this
which,
was
okay, so
wrong.
this was wrong.
So
So
in
in
Dufort-Frankel method, what
Dufort-Frankel
was
method,
done
what
is
was done is
this
simply
term was
this term
modified.
was
Instead
modified.
of
So instead of
taking
taking
phi I comma
phi
n,
I comma n,
this was
this was
taken as the
taken as
average
the
of
average of
the values
the
of phi
values
I
of
at
phi
n
I
plus
at
1
n
and
plus
n
1
minus
and
1.
n minus 1.
And that
And
resulted
that
in
resulted in
this
this
equation
equation
being
being
conditionally stable,
conditionally stable,
and
and as well as
the order of
the order of
accuracy
accuracy
became
became
second order in
second
time
order
as
in
well as
time as well as
second order in
second order
space.
in space.
So that's why the correct answer would be option B, second order. Any doubts on this? Any questions? Anything? What is one disadvantage of this Dufort-Frankel method? Does anyone know? Disadvantage of Dufort-Frankel method? Anything that comes to your mind? Any one disadvantage?
Less accurate. No?
Sorry? Can you come again? I couldn't understand.
Regarding accuracy, no, it's.
Yeah, so what happens is this equation, because of this forceful introduction of the average, this becomes inconsistent. So even if I put delta x and delta t close to 0, okay, so this would be 2 delta. Anyway, so even if we try to put them as close as 0, then also these equations won't revert back to the original parabolic equation. There would be a truncation error remaining. So this causes some issues with accuracy, because the main reason is these Dufort-Frankel method is inconsistent. Right. Okay. So let's move on. Yeah. Was anyone saying something?
No, sir.
Any questions? Any doubts?
Sir, then kindly share all these questions and solutions, sir.
Sorry?
Kindly share all these questions and solution at the end, sir.
Yeah, so the thing is, each week these videos are recorded and uploaded in YouTube. Do you have the link to the YouTube channel?
Oh, yeah, okay, okay.
No, right? I'll share one second. Give me a second.
Hello?
Give me a second. I'll share the YouTube link with you, as well as we upload the slides as well. I'm not sure whether NPTEL is sharing them with you or not. Give me a moment.
They have shared 3 weeks problem solving sessions.
Problem solving sessions, are they solving or not? They sharing or not?
First, second, third, they have shared, sir.
Okay.
First 3 weeks, these solving sessions they have shared, sir.
Okay. So I think in subsequently everything will be shared.
Okay, sir. Okay.
I'm giving you the link to my YouTube channel. You can I upload these recordings every week, so you can go through them. And there is this another TA. He is also doing the same thing as I am. So he also shares these things. So I shared the channel link in the chat box. You can access it from there.
Thank you, sir. Thank you.
Okay. Anyway, so this is where we were with question number 4. Let's move on to question number 5. So this is a match the following type of question. It has 3 questions on the left column and 3 corresponding options in the right column. You will have to pick out the correct matchings between the 2 columns. So on the left hand column we have different methods, and you have to match
You
it
have to
with
match it
whether
with
those
whether
methods
those
are either
methods are
explicit,
either
implicit,
explicit,
or
implicit, or
semi-implicit kind of
semi-implicit kind of
techniques.
techniques.
So the first
So the
one
first
here
one
is last
here is
one
last
method,
one and
option
method.
A.
Option A.
Option B is
Option B is
Dufort-Frankel method.
Dufort-Frankel method.
Option C is
Option C is
Richardson method.
Richardson method.
And on the
And on
right
the
hand side,
right hand
we
side,
have
we have
explicit,
explicit,
implicit, and
implicit, and
semi-implicit.
semi-implicit.
So which one
So
is which?
which one is
We'll
which?
have to figure
You'll
that
have
out
to figure
first.
that out
Then once
first,
you have
and then
done,
once you have
you'll
done,
have to
you'll have to
figure out the correct
figure out the correct
combination from the
combination
options
from the
given below.
options given below.
So is it option
So
A,
is it option A,
A1, B2,
A1,
C3?
B2, C3?
Is it option
Is
B,
it option B,
A3,
A3,
B2, C1?
B2, C1?
Is it option
Is
C,
it option
A2,
C,
B3,
A2,
C1?
B3,
Or
C1?
is it option
Or is
D,
it option
A1,
D,
B3,
A1,
C2?
B3, C2?
On the left
On
hand
the
side,
left hand side, we have three
option A,
options. Option A,
method.
Larson
Option
method.
B,
Option B,
Dufort-Frankel
Dufort-Frankel
method.
method.
Option C,
Option C,
Richardson method.
Richardson method.
And on the right
And
hand
on
side,
the right hand
we have
side, we have
explicit method,
explicit
option 1.
method, option 1.
Option 2, implicit
Option 2,
method,
implicit
B,
method.
sir.
B. Okay.
B.
So
Okay.
A3,
So
B2,
A3,
C1
B2,
is what
C1.
I'm
This
saying.
is what you're saying.
Okay.
Okay.
So let's see if
So
we get
let's see
any
if we
other
get any other
responses.
responses.
Larson and
Dufort-Frankel, Richardson.
are they
Are they
explicit,
explicit,
implicit,
implicit, or semi-implicit?
semi-implicit?
Semi-implicit
Means
means a combination of
implicit.
implicit and semi-implicit.
A3, B2,
A3,
C1.
B2, C1. So okay, so another response in favor of option B.
So let's have a
So
look
let's
at
have a look at the correct solution.
it is
It is
actually option
actually
C.
option C.
So why is it
So
so?
why is it so? So Larson method
Is
is
an implicit
an
method.
implicit
So
method. So
Larson
Larson method is like this. Larson n plus 1 minus n by delta t, and then we have everything at n plus 1 on the right hand side. Pi minus 1, n plus 1. Okay, so this is implicit. The Dufort-Frankel method, as we saw, it is actually semi-implicit. So here, this second term, that is taken as the average of explicit and implicit parts. And Richardson method is an explicit method, but however, it is unusable. So Richardson method, how did we write that? So n plus 1 minus n minus 1 by 2 delta t, and then on this side we have everything at n. Any questions on this? If you have any confusions regarding this, you can get it clarified now. We will have an extended discussion regarding this.
Larson method. You have some idea about that?
Sorry?
No idea about that first method A.
Method A, no idea why, because it was discussed in lecture, I'm sure.
Okay.
Anyway. So Larson method is basically BTCS technique, backward in time and central in space.
Okay.
And this Richardson method is a CTCS technique, as I told in one earlier slide. And this Dufort-Frankel method is Richardson method only, but it's a bit modified, where this n is the phi at in is written as the average of the phi at n plus 1 and n minus 1. So it's a modified Richardson method, you can say. So the correct one would be A3, B2, and C1. Sorry, A2, B3, C1. Sorry. I also repeated the same mistake. Anyway, A2, B3, C1. Option C would be the correct answer.
Does that make
things clear?
Okay.
Okay.
So
if you don't have any questions, we will move on to question 6.
So this is again
another match the following type of question where you have to match each method with its correct order of accuracy. So here also we have the same options on the left hand side. Option A, Larson method. Option B, Bruford-Frankel method. Option C, Richardson method. And on the right hand column we have the first one is order of first order in time and second order in space. The second one we have second order in time, second order in space. And the third one we have second order in time, second order in space, as well as second order in the ratio between time and space, so to say.
And in the
options we have option A, A1, B2, C3. Option B, we have A3, B2, C1. Option C, we have A2, B3, C1. And option D, we have A1, B3, C2. Okay, so we have one answer in the chat box, A1, B3, C2. That means option D, right? A1, B3, C2. Yeah, correct. So let's see if there are any other responses.
C.
So A2, B3, C1. Right?
Yes, sir.
Okay, so let's have a look at the correct solution. It is actually option D. So Larson method as Larson method would correspond to option 1. So where it is first order in time and second order in space. Now Richardson method was this. Second order in time and second order in space. Since this was CTCS, remember? This one was BTCS. Now BTCS or FTCS, it doesn't matter. Both would be first order in time. But if you take central in time, then this becomes second order in time. Now Bruford-Frankel method modified this Richardson method. So this first two terms were there. But due to its inconsistency, it includes another term which is of this leading order, that is delta t by delta x squared. So the order of accuracy of Bruford-Frankel method is this. So now if we look at it, so it will be A1, B3, C2, which is the same as option D, which is the correct solution. Okay. Any questions on this? So in one of the lectures of week 5, how to derive the truncation error in case of Bruford-Frankel method was discussed. Like how do we determine that this is the order of accuracy of this system of equations? So the entire derivation was discussed there. So basically what was done is, let's say if we write down the equation once again. So I have in Bruford-Frankel method, phi I n plus 1 minus phi I n minus 1 divided by 2 delta t. Then on this side, I have this gamma delta x squared phi I n phi I minus 1 n minus sorry. n, then minus of 2 into phi n plus 1 I plus phi n minus 1 I plus pn I minus I plus 1. So this is the Richardson method. Now, what was done is you have to expand all these terms into their Taylor series expansions, and then many common terms they cancel out, and only those terms remain except the original equation, which are of the order of delta t square, delta x square, and this delta x by delta t square, delta t by delta x square. So if you expand out each term in their Taylor series and then simplify the equation, we will get back to the original form of the governing equation, which looks like this. And then we will have terms on the ideally this should be 0, right? But we will have some terms like this of delta t square, delta x square something, then delta t by delta x square multiplied by something, plus higher order terms. But these would be the leading terms, and that's what determines the order of accuracy of any equation. Right. So this is what happens in case of Richardson method. These are the leading order terms, and this is the order. Okay. Any questions on this? All right. So we will move along. We move on to question number 7. So this is again a match the following type of question, and we have only 2 options each. So is it ADI? ADI means, what does ADI mean? Can anyone recall? What is the full form of ADI? Anyway, we will get back to that later. So the options which we have is ADI for 2D parabolic equation, and option B ADI for 3D parabolic equation. And on the right hand column we have conditionally stable and unconditionally stable. Now there are 4 options here because these are not exclusive. So option A is A1 B2, which means the first one is conditionally stable and second one is unconditionally stable. Option B is A2 B1, which is just the reverse of that. Option C is A1 B1, which means both of them are conditionally stable. And option D is A2 B2, which means both of them are unconditionally stable. Now, let's get back to here and clarify this. So ADI means alternating direction implicit. A, B, I. Right. So option B is one of the responses, A2, B1. Let's see if we get more responses. So alternating direction implicit method for 2D parabolic equation, and the same thing for 3D parabolic equation. Are they conditionally stable or unconditionally stable? The options are A1 B2, A2 B1, A1 B1, and A2 B2. The first option means the ADI for 2D parabolic equation is conditionally stable, and that for 3D parabolic equation is unconditionally stable. The second option means the first one is, or the 2D parabolic equation case is the unconditionally stable one, and that for 3D it becomes conditionally stable. Option C is A1 B1, which means both of them are conditionally stable. And option D is A2 B2, which means both 2D and 3D parabolic equations ADI applied for them are unconditionally stable. So what will it be? We have one response in favor of option B, A2, B1. Okay, so let's have a look at the correct answer, and it is indeed option B. So ADI for 2D parabolic equation is unconditionally stable. It is always stable. But ADI for 3D parabolic equation becomes conditionally stable. So there are some criteria which has to be satisfied in order for ADI for 3D parabolic equation to be stable. So those conditions or criteria are there. Okay. Which brings us to question number 8. So since we learned that ADI for 3D parabolic equations are conditionally stable. So what is the condition? What is the stability criteria? There are 4 options given here. Option A is gamma x plus gamma y plus gamma z is equal to 0. Option B, gamma x plus gamma y plus gamma z should be less than half. Is it option C, gamma x plus gamma y plus gamma z should be less than one third? Or is it option D, gamma x plus gamma y plus gamma z should be less than 3 by 2, which is 1 and 1 half. Okay, so we have very quick responses, one in favor of option B and one in favor of option D. So shall we have a look at the solution then? Okay. So the correct answer would be option D. This should be less than 3 by 2. So this is something that is obtained by any kind of stability analysis. It could be von Neumann stability analysis or any other kind. But the final result that it gives us, the stability criterion, is this. So if this is maintained, then the solution of the 3D parabolic equations by using ADI would be stable. Otherwise, it would become unstable. Okay. Any questions on this one? Okay. So we will move on. We will move on to question number 9 of today's session, which is a numerical type of question. It is asking us the maximum time step that can be used to obtain a stable solution for 1D unsteady heat conduction equation using FTCS method for alpha equal to so and so. Okay, so and so is 1 into 10 to the power minus 6 meters square per second, and the delta x is equal to 0.001 millimeter. Is what? Is it option A, 5 into 10 to the power minus 5 second? Is it option B, 5 into 10 to the power minus 6 second? Is it option C, 5 into 10 to the power minus 7 second? Or is it option D, 5 into 10 to the power minus 8 second? Now take out your pen and paper, and preferably a calculator as well if you need it. I don't think you'll need a calculator for this one. Pen and paper should be sufficient. So for the sake of solving this, it's fine. But other than that, if you look at the bigger picture, these kinds of calculations are very necessary in practical situations where you have a simulation to run. Now you're fixing the delta t, or the time step which you will take. Now that plays a crucial role, because if you take too larger time step, then this solution might become unstable and you won't finally be able to reach an actual solution. It would diverge. And on the other hand, if you take a too small a time step, then it may so happen that your calculation would take forever. Your computational cost would equally go up. Now, in order to strike the balance, you have to have some idea beforehand. So, what is the maximum permissible time step that I can take? And that would depend on the stability criteria of the kind of problem. So for that, these kinds of quick calculations are very necessary. So we have one response in favor of option C, that is 5 into 10 to the power minus 7 second. Let's see if we get any other response. Option C. Okay. So let's have a look at the correct solution. It is indeed option C. So how to get here? What are the steps? Let's have a discussion. Like, how did you get to this final solution? What are the steps that you followed? What was the first step? So the thing is we have to obtain a stable solution for a 1D unsteady heat conduction equation using FTCS method. So what is the criteria for obtaining a stable solution? In this case, 1D unsteady heat conduction equation. It's that gamma x has to be less than equal to half, right? So what is gamma x over here? Gamma x is alpha into t, sorry, not t, alpha into delta t divided by delta x square. Now this has to be less than equal to half, and we have to find the maximum time step. So if something is less than equal to something, then the maximum value of that left hand side is the actual value of the right hand side. So we will rewrite this in a different way. So we will take delta t max should be equal to half into delta x square divided by alpha. Correct. Now we will simply plug in the values. Delta T max equal to half multiplied by delta x square. So we have to do this in SI unit in order to be consistent. So delta x is 0.001 millimeter. So that would mean 10 to the power minus 3 multiplied by 10 to the power minus 3. So 10 to the power minus 6 meters is the delta x, right? So delta x is 0.001 millimeter. This can be written as 10 to the power minus 3 millimeter, and to convert it to meter, we need to multiply with again another 10 to the power minus 3. So ultimately delta x becomes 10 to the power minus 6 meters. So this is it, then square, and we have alpha in the denominator. Alpha itself is 10 to the power minus 6 meters square per second. That is already in SI unit. So one of the denominator and this would cut off, and half is 0.5. So I can write delta T max as 0.5 into 10 to the power minus 6 second, or 5 into 10 to the power minus 7 second, which is option C. So that's why it was the correct answer. So all of you did it correctly. Well done. Any questions on this one? Or anything relevant to this? If not, we will move along. We'll move on to the last question of today's session, question number 10, which is asking us match the following with respect to beta method. So Option A is implicit, option B explicit, and option C Crank-Nicholson. And on the right hand column, we have different values of beta. So beta equal to 0, beta equal to 1, and beta equal to 0.5. So corresponding to different values of beta, the actual method becomes implicit, explicit, or Crank-Nicholson. So we have one answer in favor of option D, A2, B1, C3. So to make things easier, I'll write down the beta method for you. So beta method discretization is done in this way. To phi n, n plus 1 plus phi I plus 1 at n plus 1. Then plus 1 minus beta multiplied by this same thing, but at the nth level. So this is what beta method looks like. Now as you can imagine, for different values of beta, these equations would boil down to something else. They would simplify to something else. So which one is it? So option A is, the first column, we have option A implicit, option B explicit, option C Crank-Nicholson, and on the right hand column, we have different corresponding values of beta, beta equal to 0, 1, and 0.5. Now, as you can imagine, if I put beta equal to 0, then this entire term would vanish, and only this side would remain. And since beta equal to 0, this coefficient would become 1, and then we would have only, I'll use the shorthand notation now. So I'm writing down the right hand side only. So the right hand side becomes gamma delta x square, then phi at n, phi I at n divided by delta x square. And this is what happens in case of an explicit scheme. So explicit would be beta equal to 0. And then if I put beta equal to 1, the right hand side would similarly become delta x square delta I, but at n plus 1. And that results in an implicit method where there are multiple unknowns. So implicit would correspond to beta equal to 1. And in Crank-Nicholson method, where the average is taken, so there beta equal to 0.5 in front of both. So beta equal to 0.5 in front of this first term, and similarly 1 minus 0.5, it will become 0.5 again into the explicit term. So in case of beta equal to 0.5, the RHS becomes lambda over delta x squared into the average of delta x squared at n plus 1 plus delta x squared at n
in both
at I.
So this
So
results
this
in
results in the equation becoming a
being
being
discretized by
discretized by
Crank-Nicolson method.
Crank-Nicolson method.
So
So
this is how it
this
is.
is how it is.
So what
So
would be the
what would be
correct
the correct
options? So it
options?
would
So
be
it would be A2,
B1
B1,
and C3,
and C3,
right?
right?
So the
So
correct
the
answer
correct
would be
answer would
option D,
be
A2,
option
B1,
D, A2,
C3.
B1, C3.
Let's have a look at the
Let's have a look
solution,
at
and
the
it is
solution, and it is indeed
option D.
option D.
So it was correct.
So it was correct.
So
So that ends all the questions from my side.
If you have any
If you
questions
have
from
any
your
questions
side,
from your side,
please feel free to
please
ask.
feel free to ask. If there's nothing else, then we will close the session today.
So thank you
So thank you
and happy
and
Holi.
happy Holi. Really, thank you for joining on a holiday like this.
And
Thank you, sir.
okay.
I wish you the same. Happy Holi, sir.
Happy Holi.
Happy Holi to you too. Okay.
Bye then. See
Bye
you
then.
next week.
See you next week.
Okay, sir. Thank you.
Thank you.
Okay. Thank you.